All right, today we're going to start lesson 2.8, inverses. So we have two learning goals today. Number one is whether we can determine if an inverse function will exist. And a second is to solve for an inverse function when it does exist and state any restrictions that may occur on its domain. So as we get going, a very important concept just to get right off the bat is an inverse is an expression that will map a member of another relation's range back to its domain, meaning it undoes whatever's been done. Okay, so here's the mathematical symbols for it. Let's just say y equals f of x. If y equals f of x right here, what that means is an inverse will take, if this is mapping an x to a y, the inverse would map the y right back to the x. It does the opposite. And now that we've learned composition of functions, I can tell you this. If you had an inverse function, it should map you back to x. Now you might be going, why would it map me back to x? Because this is what it would do. It would plug in an x into g and it would produce some, what kind of value? X. That's true. And g of x represents a y. This would produce a y. Well, if it's its inverse, you plug in the y. If it's the inverse, what should a y produce? X. The x. And so we started with an x. What do we end with? An x. An x. So a composition function, you would get f of g of x would equal x. It would not matter also. So I'm going to do and here. Let's go ahead and add this. If we then did g of f of x. Now this would still give us x. Let me show you why, because one more time we produce it in, and this time we would get a different y, but still it would be a y value. It would be a different y than this y. So I'll call this y with a little g there, just to say it's the g's y. This one would be y with a little f, but it doesn't matter. When you plug in the y into g, what should you get in return? X. So an inverse function will, whatever you originally plug in, if you plug it into both the function and its inverse, it'll get right back to whatever that original domain value was. This is using an x. It could be a number. It doesn't matter. It could be a 10. It could be a pi. It could be a 13. Doesn't matter. You plug in a 13, maybe you get a 25, but when you plug the 25 in, you get right back to 13. That's the point, is that an inverse will take you right back to where you were if you apply both the function and its inverse. So it says every inverse relation can be found by, does anybody know? How do you find an inverse?
Can be found by switching.
Switching, that's the word we're looking for, switching each x and y variable and then isolating the new y variable. So that's our algebra right there. We're going to switch in x and y. So whenever you see inverse, which by the way is represented by a negative f negative 1 or g negative 1, whatever, that'll tell you. Now, a very important concept to understand. I'm talking very important concept to understand. So make sure you get this. Is when we test to see if any given graph is a function. So don't read this slide yet. Before you walked into this class, if you were given a graph and I asked you, is it a function? We would do a test. What was the test called when you look at the graph? The vertical line test. Well, here we're not doing the vertical line test. We're doing the horizontal line test, because I don't care if the original is a function. I want to know about its inverse, which means when I switch the x and y. So we're going to do a horizontal line test. So a horizontal line test looks like an x-axis. And the reason I do this is because when I find the actual inverse, the inverse is going to switch x and y. So a horizontal line that looks like an x-axis, when I switch the x and y, what's it going to start to look like? I'm going to say this again. If you're testing a original graph and you want to know about its inverse, well, mathematically to find the inverse, you have to switch x and y. But if you don't want to go through the process, you can do a horizontal line test, because this line test looks like an x-axis. But if you apply the horizontal line test and then you found the inverse, you would switch x and y. So the x-axis would start to look like switch x and y. An x-axis would look like a y-axis, which is a vertical line. And so when I look at this graph, you see how there's a horizontal line test? I mean, a horizontal line? I'm not testing whether the blue is a function. I'm testing whether its inverse is a function. So if you want to make that note here, the red line, this red line here, this tests to see if the blue curve inverse will be a function. So I'm not actually testing the blue curve itself. The vertical line test would test the blue curve. But when I do a horizontal line test, I'm testing to see if the curve's inverse will be a function. Now, does this one pass the horizontal line test? It looks flat. It's actually always slightly decreasing. If you remember exponentials, they're always increasing or always decreasing. So actually going from left to right, it's slightly increasing. So yes, it does pass the horizontal line test, which means there's going to be an inverse function. That's what that means. So if it passes, we can say the inverse, you can use this notation. That means the function's inverse. That means the function's inverse is a function. So if you use that f-1 notation, that means that the inverse is a function. So you'd have the original being an f, the inverse represented by f-1, its inverse function. Okay, so there's some symbols that you'll see as we go. The next slide, all I've done on the next slide is I just wrote down the algebra. So if you want to look back at that later on, but I'm going to work through the problem. So I'm not going to actually read over this slide. That's just for you in your notes later. If you're struggling, go find that. So let's start with real basic. Now let's start real basic. What are we going to do to find an inverse? It says find the inverse relation of the given table. You would switch x and y. Now, before I just fill this in, I got a question for you. If I switched x and y, would and this y becomes the x's? Are these in order? No. So we could do it like this and just switch it where the y's become x's. And this might be helpful for your notes, just to notice that the y's become x. And what happens to the x? They become the y's. However,
It wouldn't be in proper order.
most people, or I shouldn't say most people, most times when I've seen tests, hint, the tests change the order to make sure you know what you're doing and you're really paying attention, if that makes sense. So what I would suggest you do is, let's just make sure these are in order. If I was going to put these in order, what would the order be?
-1, 0, 2.
There you go. -1, 0, 2, 2, like that. And so -1 produces a 1, 0 produces a 4, 2 produces a 3 and a 6. I'll just go 3 first, then 6. Now, as you look at this table, is this a function?
No.
Oh, wait, sorry, I forgot I added this in. Note, the original table, is this one a function?
Yes.
You'd have to ask, does it pass the vertical line test, which means, is every x unique? Do I have any duplicates of x's? No. So the original is a function. This is a function because no x's repeat. Function since no x's repeat. What about our inverse?
No. It isn't.
Why is it not a function?
Because it's only x.
So inverse is not a function since the x value 2 repeats. The x value 2 repeats. All right, so that's what you're looking for there. So let's fill in this table. The original table is or is not a function? Is a function because each x value has exactly one y value. It doesn't repeat having a second y value. However, the inverse is not a function because, oh, right here, the x value 2 repeats. The should have written it there the whole time. The x value 2 repeats. Meaning it doesn't just have one y value. The x value 2 and 2 has the y value 3 and 6. I'll go ahead and throw that in there with different y values. There you go. Whoops, y values. There you go. So that's what you're looking for with the function. Okay. Questions on that part? All right. What about example 2 here? It says find g negative 1. What does that mean right there?
The inverse occurs.
And by the way, if it's not a function, we call it a relation. So you see how on the previous problem I said find the inverse relation. Relation just means one variable produces another. It just means there's a relationship. The x's and y's do have a relationship. So they're a relation. If it's a function, it's always a relation. And even if it's not a function, it can still be a relation if as long as they're relating to one another. So there is a relationship there. So that's why we call it a relation. So over here, we need to determine first, does the inverse exist? So how would you determine if the inverse exists? You need to find out would any of these, if this is the x and this is the y, we need to check for the inverse, which column do you actually look at? The y's. You want to see, do any y values repeat? Meaning, do any y values have more than one arrow? No. So does g negative 1 exist? Yeah, I'm going to go ahead and put g negative 1 exists. And this will be our x column. This will be our y column. I'm going to keep them in numerical order, which they already are. -3, -1, 0, 4, 7. And you know what we could do just to make it easier? What does -3 gonna now point at? 1. I'm gonna change it so it's straight arrows like this. What would -1 begin to point at? This is the inverse now, so everything is going backwards. The arrows are going backwards. What's 0 point at? -5. The reason I'm doing this is really all that matters is that the x's are aligned. 4 points at 3, and then 7 points at 0. There we go. Okay, and now this one. Let me look at this. Okay, I have one for you in a second, so I'll do this one with you. Does this inverse function exist? Well, I've thrown this on because Delta Math is going to talk about this. Delta Math will just ask, do any y values repeat?
No.
Since no y values repeat, what it'll say on Delta Math is they'll say f negative 1 exists. Since no y values repeat in f of x. All right, I'll just do an f. Since no y values repeat in f, they're going to say f of -1 exists. But since 10 does not have an x value associated, they would say it's not an onto function. Not an onto function. Since 10 does not have a member, and since the range value 10, since the range value 10 does not have a domain member associated. With it. Okay, so what I want you to know is when you get to your delta math, that they're gonna ask you about onto function. That's what you're looking at. So since 10's all alone, it's not an onto function. But this would be an onto function because everything's used. If that makes sense. I'll go ahead and I'll just write onto function since every value is used. Okay, so I'll add that in there. Okay, so now let's do the inverse. When we find the inverse, you only would list the values that are used. Which values are used? 1, 3, 5, and 7. And so what's 0 going to point at? -5.
1 points to 0.
1 points to 0.
3 goes to 1. Then 5 -3 and 7 7.
And I'm just going to drop the 10 entirely. And the reason why is because the true definition of a function is that every member of the domain has one and only one member in the range. Since 10, if I put 10 over here, it would not have a member in the range, so it would no longer be a function. So I'm just dropping the 10. Okay, now you have your first DOL. Give you a moment to do DOL number 1. Also, I want you to tell me, does the inverse exist? And is it an onto function? All right, picking up. Example 3 here. Says the function f is shown. First, is the relation of f a function? So I want to know first, is this a function? How would you know if f is a function? Not the horizontal line test. The vertical line test. You'd first test with a vertical line to see if f itself is a function. So we're going to perform a test here to see, is f a function? So I pass this through. Is this a function? Does it only hit the graph maximum one place at any one time?
No.
Does it ever hit more than one location at one time? Where does it hit more than once? Right here? It actually, this would still be a function because that's forming a parabola, so those don't actually overlap. So it's actually, I would say this is a function. So f is a function because function since it passes the vertical line test. Very good. Okay, can I say VLT? I'll write that in. What does that stand for? Vertical line test. Okay. Let's talk about the inverse. We don't know what the inverse is yet. Haven't graphed it. I'm going to get this out of the way. That was my vertical line test, what I used. Second notes, I'll leave that as VLT. Okay, what about the horizontal line test for the inverse? It will not pass, it'll fail, and you can choose anyone's spot. I'm just going to choose right there about 1.5 or so. The y value 1.5. This tells us that the inverse of f is not a function. The inverse of f is not a function. So what does that mean? Let me add in, since it fails the, what test did we just do? All right, good. What that means is I wouldn't use the notation f-1. I would just say the inverse relation, but I would not say f-1 because it's not a function. Okay, so f-1 does not exist. DNE does not exist. But I can still graph the inverse relation. So how do I do so? We're going to switch x and y values. So for example, this value right there, what point is that? X and y. What's its coordinates? 2 to the right, 4 up. So if the function f has a point at 2, 4, where would the inverse relation have a point? 4, 2. 4, 1, 2, 3, 4, 2. So place a point there at 4, 2. Okay, now what about this point here? The function has a point at 4, 1. So where would the inverse relation have a point? 1, 4. 1, 1, 2, 3, 4. Okay. What about here? 0, 1, which means the relation would be at 1, 0. Okay, so this part should be a parabola. So the best you can connect those dots with a parabola like that. Okay, this arrow is going off towards, that's pretty close. It's not exact. That arrow is approximately where? What would the exact point that's almost going through? 5, 2, which would become 2, 5. So it's approximately right there. We should have an arrow going off 2, 5. Notice this one's going up and to the right. This one's going right and up. Okay, and let's see, did I give this one a good spot to, no. Well, this arrow, where's this arrow approximately at?
-5 around.
-5, 4. It's not quite at 4, so -5, almost 4, which means it'll be almost 4, -5. Here, right here, that would be the spot it would go through. And so we would draw a line going to that point with an arrow. So that's how you could draw an inverse. Notice now that we're looking at the inverse, does the inverse itself pass the vertical line test?
Yeah.
No. The inverse passes the vertical line test? No, this does not pass the vertical line test, which means this is not a function. However, would the inverse pass the horizontal line test?
Yeah.
Which tells us that the original graph was a function. Okay. By the way, if they both pass, we call it 1-to-1. I don't know if I've said that today. If they both pass, it's called 1-to-1. 1-to-1 would mean both the function and its inverse are functions. All right, your turn. I'll let you try this one. Okay, now I'm going to pick back up. But before I move on, I'm going to give you a trick. I say it's a trick. It's not really much of a trick, but to see if you got it right, I'm going to go back to the problems we just did. Using this problem, if you test what should happen on an inverse, let me copy this because I'm going to move it. What should happen on an inverse is that it can be reflected on the line y equals x. And here's the reason. An inverse means you switched x and y. So if I'm switching x and y, sorry, let me see what I got chosen here. If you're switching x and y, the only spots where the graph would not change is the line y equals x, because literally that means the y is equal to the x. So for example, the point 1, 1, when you switch 1, 1, what do you still get? 1, 1. If you switch 2, 2, what do you still get? 2, 2. So this should be reflecting on this line, because on that line itself, nothing happens. If you had a point on that line, nothing would happen to the graph. But what does happen is the things that are above get reflected across to the right. Things that are on the right get reflected above because you're switching x and y. So notice I'm using the words right and above. Above means a y value that's up. Right means an x value that's to the right, obviously. And the things that are to the left get reflected. Things that are on the left get reflected below the x-axis. Things that are down below get reflected to the left of the y-axis. So anyways, let me now add that to this line as well. Here's the line at y equals x on both of these. You can check to see, does the reflection look right? Does this piece that's on the right get reflected above? Yes or no? Speak up for me. The piece to the right, did it get reflected above?
Yes.
The piece to the left, did it get reflected below? Or you can think of this way. The piece above, did it go to the right? Yeah, it does. And so that's how you can test to see if that works. That's the line y equals x. If you want to add that, use your ID and draw like a dashed line diagonally through there. That's a great test, especially on your DOL. To check to see if you got it right is you could throw on that line y equals x diagonally through here and through over here and check to see if it reflects properly. Again, the thing that's above's a y word, becomes, if the graph is above, when you reflect it, where does it go? If you reflect on the line y equals x. If it was above, it becomes, that's a, no, not a below. If it was above, you're reflecting it, meaning you're doing its inverse. You're reflecting across y equals x. It's no longer an up and down word, it becomes an x word. If it was above, it goes to the right. If it was below, it goes to the left. Or if it was on the right, it reflects and becomes above. If it was on the left, it reflects and goes below. That's how inverses work. Again, above goes right, below goes up. I'm sorry. Above goes right, below goes left, or you could think of it as left goes below, right goes above. Okay, so you can think of it either way. All right, moving on. Example 4. Now let's get into some algebra. It says, is the inverse of f of x equals x squared minus 3 a function? Why or why not? So let's think about, what is f of x equals x squared minus 3? What's that graph going to look like? You didn't know these by heart by now.
A parabola.
A parabola. Now,
3 spaces to the right.
okay, is that inside or outside? So it's actually going to be going down, okay? So here's a little x-axis, y-axis. Here's a little graph. Let's do a sketch. This would be a parabola shifted 3 units down. 1, 2, 3. We're graphing that using the leading term and a transformation. So there's our graph. Here's the question. Is the inverse a function? Why is the inverse not a function?
Because it touches twice on it.
Yeah, f negative 1 does not exist. Said another way, the inverse of f is not a function since it failed. F fails, not it, let's say, since f fails. What test did I just do right there? The horizontal line test. Okay, nevertheless, just because the inverse is not a function does not mean we cannot find its inverse, especially with domain restriction. So what does domain restriction means? It means, let's take a picture, let's take a look at this graph and cut off the graph to where it only exists with the domain of 0 to infinity. So here, I want you to draw another little quick sketch, another brief sketch here.
Wouldn't it just be on y 3 and then go down to the right?
Okay, so we're about to get to that, but first, this is domain. So domain means which values? X. So we're going to take the same graph, go down 3 units, but now we're not going to let this part of the graph exist. This part is restricted. Okay, so I'm crossing that out, saying we're restricting that part of the graph. So what's left over is a parabola going to the right. Does that make sense? What we're doing here? So now, would the inverse function exist?
Yes.
Yes. So here's how you solve for it. You switch x and y. Switch x and y. These steps were given to you earlier in the packet. I skipped over the slide. I don't know if you remember. Hey, Chris, make sure you're with me here. So I'm going to switch x and y. In this problem, what represents y? That's right. Y equals f of x. So we're gonna say this equation becomes x equals y squared minus 3. Because y is the same thing as f of x. When we graph, that's y, f of x is represented by the y's. So I first switch x and y. The second step is you isolate the new y. Isolate the new y variable. Okay, so what would I do first here? Add 3. So x plus 3 equals y squared, because we did the opposites. Y was being subtracted by 3. What's the opposite of that? Adding. Okay. Now, is y isolated? Not quite. It's squared. What's the opposite of a squared? Opposite operation. We need to take a root. Now, typically, when you take a root that's not originally there, you need a plus or minus. Typically, we need a plus or minus, but let's go to the restriction. When you look at the restriction, so if you forgot, a square root is a half of a parabola. This graph, it was a full parabola, now it's only a half. Which side are we taking, the negative side or the positive side? Okay, so go ahead and make a note here. We're not going to use this negative side. This part got restricted out. So we're not taking the negative square root here. We're only going to take the positive. So I have y equals, these two cancel each other, by the way. Y equals the square root of x plus 3. That's going to be my inverse. The third step, and on the textbook earlier, they listed as 4. I'm going to do it as 1, is it says you exchange the y, replace y with, what's the symbol if it's a function after being restricted? With function notation, yeah, with f never to 1. So I'm going to say, and I'm going to put these together because you really need to do them together. And state restricted and state restriction. And so the only reason this is a function is because we're going to say f negative 1 of x equals square root of x plus 3. Now here's the restriction. I'm not going to necessarily say it's 0 to infinity anymore.
Just say all numbers but 0.
No, that's a good thought. It goes off of the original's range, because the range becomes the x values. How low did this value go? Negative 3. Where we're going to say x is, it goes from negative 3 all the way up to infinity. So I'm going to say x is greater than or equal to negative 3. Other than that, it's all real numbers. And so that's my solution right there. Now, if you want to make a note, because there's nothing there to tell you, this came from the original's range. Originals. All right, let me not say original. That could be confusing. How about this? F. F's range after restriction. Now, this would have been the same range even before the restriction, but I'm going to put that after the restriction. So that's where that came from, was this one's range. Why not include that over here as well? The range was a negative 3 to infinity, and so that's what this is here. All right, a question for us to consider here. If the domain had been restricted to negative infinity to 0, let's think back through this. If I did not restrict the left side, what if I restricted the right? Would our inverse in part B been the same answer? What would have been different? If we only had the negative side, we would have taken the negative on the root. Does that make sense? Yeah, so go ahead and put in here no, and we'll just go ahead and write the answer no. What would have happened is we would have had f equaling negative square root of x plus 3. We would have taken the negative answer, not the positive, but the negative, because of if we had the negative domain. Does that make sense? the range would still have been, the domain still would have been the same. Domain still would have been the same because the range wouldn't have changed. It still would have gone as low as -3 and up to infinity. So that still would be the same. The only thing that's different though would be the equation. Now, I want to make sure you agree with me on this. Make sure no one's confused. So I'm going to pause for a moment and show you this visually. A lot of you are going to be doing this stuff on homework, so we could use our calculators. I'm just going to use Desmos. What I did on, where's internet? There it is. What I did on your AP Classroom, let me go there. Maybe I'll go there. I want you to know, as I linked the calculator, if you click on inverse functions here, I went ahead and linked a calculator that I created so you can see this play out. But I'm going to show you from scratch just in case you ever want to do it from scratch. You can do it that way as well. And I'm going to show you how to do a restriction. Goodness, my computer's going slow. Go ahead and open up Desmos for me, and then we'll do Inspire after. Come on. What is taking this so long? Okay, well, while that's loading, why don't we just do the Inspire first? Here's what I want you to do. Go open a new document. Don't save. So make sure, I want to get everything else cleared out. So when you type in the buttons I tell you, it works. Hey, Chris. Make sure you're with me on other things. All right, I want you to go to add graph. The original function they gave us, I have forgotten. What was the original function they gave us?
Squared minus 3.
X squared minus 3. Great. But we had a restriction. To restrict a graph, this is very important. You know how to do this. You need to hit Control equals.
And the line.
It's the line. It's the one that does not seem to belong with the other inequalities. This one's telling you to restrict the graph. Now, it's not absolute value. So that's one of the things I've seen students do wrong over the years is they think of this like absolute value and they do 2 of them. We're not doing 2 of them, only doing 1 here. That's telling the calculator we're going to restrict. We said we needed to restrict from what values originally? Whoops.
0 to.
That's right. So I'm going to do X is greater than or equal to 0. Once you do that, press enter. And you see the graph? Okay, so something you can do on your calculator that will show you what the inverse should look like in case it's a calculator operated problem is this. Press menu and choose graph entry, and I want you to choose a relation. We're going to always do this part in relation just because, number 1, inverses aren't always functions, and 2, what we're about to type in won't work on the function menu. So choose relation. Now here's what we're doing. We're switching X and Y. That's what an inverse is. So, and you see how this says F1 of X? Well, usually we would say the Y is equal to, and my calculator says F1. So that's what the normal function would be. Y equals the F of X. But we're wanting the inverse. So what do you change on the inverse? What gets exchanged?
The Y.
The Y and the X. And I'm actually going to do this on relation 2 so it has a different color. So I'm going to delete that. I'm going to go to relation 2 so it'll not be blue. So what I'm going to type in is X equals F1 parentheses Y. So this should show me the inverse. It'll take this function and it'll graph the inverse. It'll just switch X's and Y's. Notice, what did we get here? Does that look like half of a sideways parabola, meaning a square root? Yep. Is it shifted left 3 units like we said it would be? Because it took this one's range and that range became, this is domain. See how that worked? Now, check this out. Let's go back. Let's edit F1. Remember part C where I said, question to consider, what if our domain had a different restriction? Go ahead, double click on F1. Just highlight it, click on there, so that pulls up that equation. Or you can go to menu, graph entry, choose function again, and edit this. And this time, let's make it where x is less than or equal to 0. So we're going to change our symbol to less than or equal to 0 like that. Now, what should this restriction do instead?
Just opposite.
Instead of it going to the right, now the parabola should go to the left, or half parabola. Okay, when it goes left, our inverse also changed automatically. But check this out. Did my domain actually change?
No.
No, because I did not change my range. I changed my domain, but that doesn't matter for inverse. It's the range that matters. And since my range did not change, the domain didn't change either. Kind of cool, isn't it? All right, I'm going to take a picture of this for the sake of notes. So let me come back over here really quickly. And I'll add this back in here later. Okay, and I don't know if my Desmos came up, but we'll do part B, our example 5, and we'll try Desmos for example 5. Let's continue on. Now it says part A, if the domain of g of x, what type of graph is this going to be?
Parabola.
Parabola. I know it'll hit the y-axis at positive 36. That's the y-intercept. How could we figure out where this has a zeros? Go ahead. What's the technique to figure out where we have zeros here? X method. You need to remember how to do this. So I'm going to walk you through this one more time. So if you want to know where does this have zeros for graphing sake, do X method. Factors of A times C. Go at the top of this X. The coefficient of B goes down there. So B is negative 12. What is 1 times 36? Okay, what are our two side numbers? Factors of 36 that add to be negative 12.
3 and 12.
So there's 3 and 12, there's 1 and 36, 6 and 6.
Yep.
Okay, to make them be negative 12, you're saying both negative? We'll check it. Is a negative times a negative a positive 36?
Yeah.
All right, we're good there. So you split your term, A terms power. And so g of x would become x minus 6 times x minus 6. Is there another way we could rewrite this?
X minus 6 squared.
All right, now we know how to graph that. Tell me transformation. It's still a parabola. Tell me what we know about with transformations. 6 to the right. Y to the right. It's with the x on the inside, and x is a liar. 1, 2, 3, 4, 5, 6. And so it's going to hit right there. That's at 0, and it's going to have multiplicity there, which means it doesn't go through the x-axis.
It goes like a little.
It's going to make, it's going to bounce off of it. So this is a positive parabola. So the parabola should come in and go up, but there's a restriction. Which way am I restricting it to? The left side or the right side? I only want the left side. So draw in a left parabola. Whoops, kind of missing there. The left parabola there. And you're not going to have the left side. So that left side is gone. If I did it, you can see that's where it would be, but it's been restricted. So this side, actually I'll do it like this. That is restricted out. Restricted out. Okay, so here's the question. The solid portion. Is that a function? Is it itself a function? Does it pass the vertical line test?
Yeah.
Yeah, that's why it uses this notation. What about its inverse?
Also, no.
Yes. The inverse would be a function. When you restrict this part out, the restricted g is a function. It's inverse, I'm sorry. G negative 1 is a function with the restriction on G. I should say the domain restriction. The domain restriction on G. Okay, before I move on, what's gonna be the range of this? How low does that go?
Zero
And
to
infinity is 6.
No, how low?
zero.
0, how high?
Oh,
Because this is going to be the inverse domain. All right, so what's our steps? What's the first thing we need to do to find our inverse function? Switch x and y. Now, which function do you want to use? We could use the original here, or we could use this one. You want to use this one? I agree, it'll be easier. So instead of this is y right here. So I'm going to say it's x equals y minus 6 squared. Walk me through.
Square root x.
We square root x. Now, when you add a square root that's not originally there, it's supposed to have
plus or minus.
a plus or minus, but we have a restriction, so we're not going to have a plus or minus.
We're gonna have.
Which side got cut off, the positive side or the negative side? Yeah, the positive side. So this positive side is restricted out. So that means we have negative square root of x equals y minus 6. Last step.
So negative square root of x plus 6.
You know what? I forgot to do a step 2. Step 2 is when you start isolating for y. We're doing that. And so, sorry, y'all said plus 6. Plus 6 to both sides. Does the plus 6 go inside the square root?
No,
that's
Why not inside?
because
It would not be adding 6.
math.
Yeah, it would not be adding 6 if you put it inside the square root. Would no longer be a 6. So there's my equation. So once I have that done, I'm going to rewrite it. Step 3. Instead of saying y equals, we're going to say use the function notation. So g negative 1 of x equals negative square root x plus 6. And what's our domain?
Domain's the same.
So
No.
negative 30 to 6.
Not negative 3 to 6 or negative infinity to 6. I'm sorry, that's not the domain.
Oh.
It's going to be this one's range.
It's gonna be 0 to 0.
0 to infinity, or you could say it this way. You could say x is greater than or equal to 0 x e double r. There's your answer right there. See if my Desmos ever loaded, so I can show you how to graph this with restrictions on Desmos. It did load, great. The function g of x is x squared. I'm going to this time do the original since the calculator is doing the work and make sure I didn't mess up. Plus 36. Now, if you're going to restrict on Desmos, here's how you do it. You do the squirrely bracket like that. That squirrely bracket is how you do a restriction on Desmos. Now, what did they say to restrict it to here? Was it negative infinity to 6? Desmos only uses inequalities. It does not use what's called interval notation like it was given. So what that would mean is that x is less than or equal to 6. That's how you type that in. Okay, so there's our function. Is that what we were expecting to see? A half of a parabola that stops at 6? All right, and so then from here it's the same. G of x refers to the y. So you see how that's the same graph right now? If y is g of x, so it's the same graph. But what do you do to get an inverse? Come on now. How do you find an inverse? Switch x and y. So if y equals g of x normally, to find the inverse, you want to type y equals g of x, you type in x equals g of y. And now that's what it would look like. It's an upside down sideways parabola, which means it's a negative square root. And you can check your answer, negative square root x plus 6. That's what we got as our inverse. Does it work out to be right? Does it? You bet. Now tell me about the domain. How far left? No, that's how high. That's how far left? 0. And went to 0. That's right. So you can see that our math actually worked out right there. Alright, I'm gonna copy this in before I move on. And I'll fix that later. Alright? Are you still copying something?
No.
Alright, good. I'm sorry. Let me shrink it then so you can copy. Tell me when you're good. All right, so I have a DOL for you. I'll let you work on this one. All right, example 6. Let's find the inverse function for each of the following. Let's start with here do y'all remember what this is called? It starts with an R. We have a fraction equation. What do we call that? Rational. So what's our steps? What was the first step algebraically that we did? What? Try that again. I don't know what just happened there. What's the first step you do when you solve for an inverse?
Do the opposite of what function is showing.
You switch x and y. So this is y equals f of x. So it becomes x equals y minus 2 over y plus 3. Now we need to isolate the y's. This one's weird because there's multiple y's. You have to stay with me. So here's how you're going to do this. Whenever you have multiple y's, the first thing I like to do is to get rid of the fraction. How do you get rid of a division or a fraction? Multiply. So I'm going to multiply by the quantity y plus 3. Y plus 3.
So then it'll be x.
So those will simplify. What do I do here when I have a parenthesis multiplying? Distribute. So I will have y times x, which I'm going to rewrite as xy. I'm going alphabetical order. Plus 3x equaling.
Y minus 2.
Okay, what you do if you have multiple y's, once you get rid of the fraction line, you group your y's together, and we're going to do a factor, a GCF. So I'm going to get my y's together on one side, anything that does not have a y on the opposite side of the equation. Do y'all want to move the xy to the right, or do you want to move the y to the left? Which way do y'all want to do it? Doesn't matter.
The Y to the left.
Okay, let's move this y to the left. The opposite of a positive y is a negative y. So I will subtract the y over here. Now I need to move the 3x to the right to get the y's isolated. So what's the opposite of a plus 3x? And we're going to subtract 3x. Those simplify, these simplify. So I have xy minus y. I cannot combine those. That's an xy. That's not the same thing as just a y. Equals a negative 3x and a negative 2. I'll put the negative 3x first. Doesn't really matter. I'm just going to do it that way. Now here's the trick. A lot of students get stuck once they get their y's together. The trick is to do a GCF. What did GCF stand for? Do you remember? Okay, what's the common factor on the left side? Y. It's the purpose for what we did. I can factor out the y. So if I divide out this y, I'm left with x minus, what's y divided by y? 1, good. Equals negative 3x minus 2. Now, if you get here, I'm convinced everybody will get the right answer. What's the only thing left to do to get y by itself?
You would divide by x.
Divide. And you don't need the parentheses anymore. The division will serve as a parenthesis in itself. And that is our inverse. So we're going to say f negative 1 of x would equal, by the way, we didn't test this, but it is an inverse. Negative 3x minus 2 over x minus 1. Or if you don't like the negatives, what you can do is switch every single sign and it's still equal. It's like multiplying through a negative 1 over a negative 1, which would be positive 1, multiplying positive 1. So I could rewrite this. If you don't like negatives, you could rewrite it as positive 3x plus 2 over. Now both of these signs would switch as well. So I would now do 1 minus x. You could do it that way as well. To list the domain, The original domain was x cannot equal -3. Will that be the same thing over here?
No.
No, that becomes the range. Just to make sure y'all know, that's the range, is that y cannot equal -3. But for the domain's sake, just think of your rules. What are you not allowed to do with divisions?
Not equal to 0.
Okay, can't divide by 0. What would give you a 0? If you looked at it this way, 1. What about over here? Would that be the same thing? 1 minus 1, would that be 0? X cannot equal 1. There you go. Other than that, x can be, you can't divide by 0. And I could do y is all reals other than -3 as well. You could go graphically test this out, but that's how it works right there. Both of these, now where did I get the range? Great question. I got it from the originals domain. Remember, domain becomes range. We have not added those in previous ones, but since it was so easy, I went ahead and just added in there. When you switch x and y, it becomes the range. All right, I have one more. And we'll wrap this up. Yep. Part B. Let's walk through this one more time. This time I want to be a little bit more guided, which means rather than me leading you through, I want you to kind of guide me through it. And I'll make sure you don't mess up along the way. What would you do first?
Switch x and y.
That's right. So I want to say that's y equals there. So step 1, I don't think I ever wrote step 2. Oh, I didn't write any of the steps. So, all right, I'm good. Switch x and y. X equals 2y plus 1 over y minus 3. Good. That alone is step 1. Step 2. That's right. We want to isolate, we want to isolate our y value, which the easiest way to do that is to first get rid of the rational function portion to get rid of our denominator. So that's simplify. What do you do mathematically with the parenthesis next to a variable? Distribute, multiply. Y times x. I'm going to reorder and say xy, and then -3 times x. Okay. Now what? We want to get our y's together on one side. So I heard add 3x first from Alexis. I agree with that. Because that does not have a y, we want to move that away. Subtract 2y. This will group our y's together. So I now have x, y minus 2y equals 3x plus 1. Good. What type of factoring? GCF, the best kind. So what's common here is a y. When I pull out the y, I'm left with x minus 2. Great. Yeah, that's multiplying. So the opposite is to divide. Once you divide, you don't have to have a parenthesis anymore. And just like that, we have our answer. This one said g of x originally, so the function notation would be g -1. I should say the inverse function notation would be g -1 of x equals 3x plus 1 over x minus 2. Now, we have to get our domain from here or get it from the range there. Since the range is not given and we did not graph, let's just think of ourselves. What would the domain be here?
Cannot equal to 2.
That's right. It can be any other real number. It just cannot be 2. And the range, we can just pull that from above. The range would be not equaling 3. But y could be anything else. We had, I don't know if you remember your rules, since that earlier we had a Bobo bot in Eats DC. Since the exponents are the same, you would divide your coefficients. That's why it's 3. It's because it's 3 divided by 1. That would be the horizontal asymptote. And just like that, we have our answer, which brings us to our final DOL, one for you to try all on your own. How about this? What I did on your DOL is I thought you had a lot of inverse practice, so I thought I would combine this with compositions. I've given you a graph F, and here's the equation G. I want you to find G of, what does F negative 1 mean?
Inverse.
G of F's inverse of 2. Which I want you to think about that as, what are you doing with the 2?
Right, putting it in.
It's the inverse of F, which means I'm not actually giving you an X here. Think on that. That 2 would not actually be an X. What is that 2 actually?
Oh, wow.
Because you're gonna, because given F's,
Oh, because you're giving me a one.
yeah, there you go. I'll let you think on that.